Okay, so if you actually look at the general structure of penicillin, yeah, you see that the first thing you see is this bicyclic ring structure. Yes? Okay? And they actually made up of one 4-membered ring, yeah, and the other is the 5-membered ring. Okay? So the 5-membered ring is called the thiazolidine ring. Okay? And then it's fused with the 4-membered ring. Okay? And this ring is called the beta-lactam ring. Okay? Okay. In this case, if you actually see, yeah, you have also the carboxylic acid side chain on the side, all right? And there's also this acetyl amino side chain as well, right? So in terms of chemistry, so now we're going down, we're going behind the scene again, yeah? So in terms of chemistry, yeah, we actually going to, let me just see whether I can do this or not. Okay, so in terms of chemistry, the most important part of the molecule is actually this, the fused bicyclic ring. Yeah, so the most important part would be the this part of the ring. Okay, that's dimethyl, that's the carboxylic acid. Yeah, all right. So in a sense, these are the one that will be determining the chemistry, most of the chemistry of penicillin. Yeah, okay. The one that you see also, the part that is important would be the acetyl amino group, and this part is actually very important in terms of improving the pharmacokinetic, improving its resistance toward beta-lactamases, yeah, or transpeptidases. Yeah, this is to improve the pharmacokinetics, meaning that whether it's metabolically is more resistant to what the metabolism or excretion in a sense, yeah, and also in terms of improving the resistance towards lactamases. Yeah. Okay, so that's with penicillin in a sense, in general. Yeah, the carboxylic acid side chain are usually also for more on the pharmacokinetics. Yeah, improvement. Not so much on the chemistry really. Yeah, compared to cephalosporin. Yeah, they are more towards the lucilator in a sense. Okay. In terms of numbering, now you see so many things in there. Let me just see whether I can delete this. Let's delete this and this one as well. Oops. In terms of numbering, which is very important, yeah, I always, well, not always, almost every year, yeah, I would actually ask how's the numbering for the penicillin, actually, the molecule. So the way actually I do it, if you see the numbering starts from the sulfur groups, yeah, so from there, and it goes to the carbon ring, the dimethyl, number 2, yeah, 3, 4, 5, 6, 7. So in the numbering for the ring would end actually at the carbonyl. Okay? Alright. And the numbering for the side chain, yeah, usually you have 1 prime, 2 prime, and so on. But it is not too critical. Yeah, the most critical I think would be usually we're talking about the central ring, the bicyclic ring. All right. Okay. So there are a few types of bicyclic fused rings. Yeah. You can see here actually. There's again, this is Panam. Yeah. This is what essentially the penicillin. Okay. This is Panam when you have the alkene, yeah, in the ring, in the thiazolidine ring, yeah. And when you actually replace the sulfur with a carbon, that's a Panam. That's a carbopanam. I don't know if you can see that. That's a carbopanam. Alright? Okay. And if you have a ring, you have just a 4-member ring without this 4-member ring at all. Yeah. So this is called a monobactam. Yeah. And essentially, a monobactam, yeah. If you see this, let me just sorry. If I can just zoom down to monobactam, yeah. If you see this monobactam, yeah. What is that? Just talk about just how minute. Talk yourself. Yeah. Think and interact with it. Come around. Actually, yeah. But the one who knows, and this is when you have N, yeah. When you have N, next to that you have a carbonyl. That is called an amide bond. Yeah. And amide bond occurs all the time in amino acids. Yeah? Okay? In amino acids, in peptide. Yeah? So this is a way to link. So in this particular case, yeah, this is a ring, yeah, which we call a cyclo. Yeah? And it's 4-member ring. There's 1, 2, 3, 4. So this is cyclobutane. Yeah, the carbonyl starts with nitrogen. I assume that you know the priority as well, the numbering in terms of numbering priority. So 1, 2, 3, 4. So this is 4 own. Yeah, aza means there's a nitrogen in there. Yeah, so it's 1 aza. This is 1 aza cyclo as a ring. Yeah, so 1 aza cyclo butane 4 own. Okay, right? So it's actually the essential part of beta-lactam. Okay, let's go deeper. One level deeper. Yeah. So listen to me now. If you want to discuss, there is time for discussing. Okay, so listen to me. Now we're going deeper, a level deeper. So what do you think the ring would be like? Would it be in a very unstrained position or very strained position? Who says strain? And I see hands. Strain. Okay, 1, 2, 3, 4. The rest I'm not sure. Okay. A. Unstrained, relaxed position. No pressure, basically. Who says A? Hands up. Who says B? Strain. 1, 2, 3, okay. Q, less than 20. Now we are at 25. Okay. More? Who says, I don't know. Okay, I assume the rest I don't know. Yeah? Okay, let's go back just for a while. So, you have learned actually before, and I will actually also highlight again. When you have a cyclohexane ring, yeah, cyclohexane ring. Oops, yeah, ring. This is the most relaxed. Why? 1% perhaps. Purple today. So, so the one in the middle. So have 1, 2, 3. The third one. This is the deepest purple. Why? Tomorrow she said I'll be wearing something else. What do you think is the most relaxed? It's a shout. Say again? Can everyone just be quiet? We want to hear from her. Is that your chair? Eh? Decomposition. Like a chair, okay. So what? Which kind of chair? So it's like a chair, yeah? And the angle between the carbons are about 120? 109 or 109.5. Okay? I take it as it is. Yeah? So one of your classmates said that between these two angles, is about 109.5. It's quite big. Yeah? You compare now with the cyclobutane. Yeah? So the angle here is, you see, when I say angle, this would be usually hydrogen, yeah? And you have carbon here, this is a carbon, this is carbon. Yeah? Think again in terms of orbitals. I think probably, think again in terms of orbitals. The electron clouds from here, if you have electron clouds from here, yeah, they are closer, yeah, they're almost touching each other compared to here actually. Here they are away, so far away compared to here. Okay? Therefore, this is more strain. Okay? Secondly, as well, when you have a bicyclic fused ring, yeah? So if you have, if you have a ring like this, for example, and another one fused at only, hang on, let me just, oops. Oops. I cannot seem to actually delete the rest, so I have to delete the, oh well. Playing around with technology again. So if you have, say, example, a ring, say again a cyclobutane, or butanol, butanone, yeah? And if the fusion, yeah, the linkage is just at the end here, so you say they have like that, yeah? Okay, so this is okay, in a sense. This is a bit strained, yeah? And here is a bit strained. This is, the 4-membered ring is more strained than the 5-membered ring, okay? But the electron clouds are actually far away. They're just between that and here with that. It's not too, it's actually too far away, in a sense, yeah? However, if you have something like beta-lactam, this phantom, So when you have something like a fused bicyclic ring, yeah, so now it gets into a double trouble, in a sense. Yeah. So one, why? Because the first one, this is already strained, very strained. Yeah. This is very strained. And what happens is that when you have a second ring coming in, yeah, this ring, yeah, even these two rings actually, this fused cyclic ring, they no longer be flat. You probably see it from the top, like this is flat, yeah. But once it's actually becoming bicyclic, it's no longer flat. It's bent a bit, yeah. You see more. I'll talk about this more tomorrow. Okay. Okay. So just a little bit about penicillin. So the first penicillin is benzyl penicillin, penicillin G. Okay. And they actually use it in World War II. All right. And it's actually mainly used for gram-positive infection. Yeah. So here, what's missing here is gram-negative. It doesn't work. Penicillin G, yeah, Pen G doesn't work against gram-negative. Not so good. Yeah. The good thing about penicillin is that it's non-toxic. This is very important. Yeah. So what happens is that in the World War II, because at the time, there's a lot of needed for soldier, all right, and the supply is limited. So what happens is that when somebody's probably got their leg amputated and so on, they got injected with benzyl penicillin. Yeah. Notice I said injected, yeah. All right. And then also what happens next is that when the soldier urinate, the nurses will fill out the urine of the soldier just administered with a penicillin injection. You evaporate all the water and they re-inject it into another patient. Yeah? Because it's given by injection, yeah? So literally is non-toxic and is also excreted in urine. Almost as is, so it still can be used and it needs to be recycled, and that's how they recycle it during World War II. Yeah. Synthesize. So at the time, they have this huge industrial production of penicillin, and the first way is actually they actually fermented. They produce it by fermentation. Yeah. And what they get is this 6-APA nucleus, yeah? This 6-APA nucleus, so this is the nucleus, this is the main nucleus of penicillin, yeah? And they react it with phenylacetic acid to form penicillin G. That's how they synthesize it firstly. It's through the semi-synthetic way, all right? They can also then, from pen G, what happens, they can actually then do an enzymatic removal, yeah, of the side chain. In this case, I use pen G, yeah, and get again the 6-APA and then acetylate with different suitable chains, different side chain. As again, if you remember I said earlier on, the side chain is to improve the pharmacokinetics and to improve the resistance of this particular compound, penicillin, towards enzymatic attacks, to be more resistant toward the lipolysis. Yeah? Okay. Again, as I said earlier, notice that I said pen G was injected. Yeah? Because if it is taken by mouth, yeah, it would actually decompose. Okay. So we can actually have a look at, why is it decomposed in a sense. Okay. So in terms of the pen G, or the penicillin molecule in general, there are two types of decomposition or deactivation. Yeah? The two instances, one that bends, it just bends the molecule further. Yeah? Another one that breaks the molecule. This is very important. Yeah? So the first activation, deactivation or decomposition of penicillin would actually occur when you have actually this beta-lactamases, the enzyme. Alright? I wouldn't go through this. I think pharmacology will cover it. Yeah? The different mechanisms and so on. Yeah? So with enzymatic involvement, beta-lactamases, transpeptidases, and so on, what happens is that this part is very important. Yeah? This part is very important, whereby when you have penicillin, this ring, the beta-lactam ring, is broken, gets ripped down, yeah? Collapses basically, yeah? Opens up in a sense. Yeah? So once it opens up, it would then form this penicillic acid. Yeah? This is very important in a sense. Just a simple meaning that you have, again, the original structure, you have carboxylic acid and you have this minor group. Just a simple ring opening. Okay? And then an alternative route taken by this molecule will be a rearrangement into a simpler decomposition to the simpler molecule. So what will happen is that this, once it's broken up, yeah, once this is broken up, yeah, it will then get further. I don't know whether can you see it. This is the carboxylic acid group, yeah, that's from the ring. It will get broken up. This ring, I wouldn't show it here in a sense. Once you have this going into here and the ring broken up, and again this ring broken up, so you get this opening of big molecule. Two rings are open now. One is the lactam, another one is the thiazolidine ring. Okay? And further, that part will collapse and form carboxylic acid. So carboxylic acid will be released in a sense. Yeah? And this once is, this is now, remember, this is now charged. Yeah? So once it's charged, you can actually then reattack into the double bond. Yeah? Okay? And then you form the penicillic acid. Yeah? And also the aldehyde as well. Penicillyl aldehyde. And the penicillamine as well. Yeah? So if you see all these byproducts, penicillic acid, this penicillyl aldehyde, and the penicillamine, yeah? These are no longer active. Yeah? These are no longer active substrate. They no longer have any effects on the bacteria. Okay? So this mechanism is very important. Okay? Let me just show you. I have another 10 minutes. Okay. Let me just show you. Yeah. Just a picture of almost the real thing. This is a model of beta-lactamase, yeah, with PenG. So beta-lactamase actually look like that. That's beta-lactamase. So it's not a square that you will see. It's not a square. It's not a round thing. It's got it's got the hexes. It's got the beta pleated sheets and so on. Yeah. And so now, if you actually just zoom into this area, yeah, going to zoom into this area. So you've got now the zoom area. You can see that this part of the molecule, penicillin molecule, is open up. All right, and around that are the sheets and the different hexes, and these are the one. This is the active site. Yeah. So the active site that you're actually seeing are not none of the squares now. Yeah. It's just full of amino acids. Yeah? But coming back to the schematic diagram, if you ask in exam, if you ask in exam to draw penicillin inhibition schematically, this is what you should draw. Okay, so whereby what you have here, so just draw, maybe I probably just give you, maybe in a quiz, I'll probably just give you an empty one, like 1, 2, 3, and just to show you the active site, and then I'm going to ask you, okay, firstly, how would actually penicillin bind to the active site? Okay, and second is that show me how, using a curly arrow, this curly arrow, how would actually the ring opening occurs. Do you think you can do that? Do you want to do that? Now? Yeah? Or shall I move on? So which one then? Do you want to do that? Yes? Yes? So, take down all this in a sense. Have a look first. So basically, what happens here? Let me just go through with you one by one, step by step. So the first step, actually, is whereby in a transpeptidase enzyme, in the active site. So this is the active site. So you have serine. You have a lot of amino acids around. So all these here, as I showed you earlier, there's a lot of amino acids around. But the one that is, there are two that involved in the mechanism in this particular thing. There are two, just two. First is serine, second is lysine. So serine is the most important one out of the two. Because serine having an alcohol group at the end, the terminal end on the side chain, will actually attack the four-member ring. So you actually go in, so you just zoom in again. You actually attack. So serine having these two lone pair, you actually attack the ring at the carbon-carbon now. Please don't show me. A lot of students previously would show me that you can use one of those as a method. So they show me like this. That is wrong. The attack always goes to the carbon, the more electrophilic. Here, this is the nucleophile, and this is the electrophile on the carbon. Okay, so attack is always from nucleophile to electrophile. So these attacks with lone pair to the carbon, and then this usually go in, go out. The electrons actually will be driven out, and it will then back in again into the carbonyl ring, and only then this ring, this bond is broken down. Is it clear on the first one? Yeah? No? Yes? Confused? Who say confused? Who's confused? No? Okay? Shall I move on? You know what? Why don't you? I'm going to go around and see how you're doing. Okay?